Hello and welcome to this video where we're going to be taking a look at my approximation to the prime counting function. So let's get right into it. Okay, so to kick things off, what is the prime counting function? Well, the prime counting function is something that counts the number of primes less than or equal to some real number x. For example, if we put the number 5 into the prime counting function, and the prime counting function is known as pi of x. So if we put 5 into pi of x, then we get 3, because there are 3 numbers less than or equal to 5 that are prime numbers. And there's no accurate closed form expression for pi of x, because no one's created one. And it's not very clearly known if there is even one. And many people assume that there isn't one. But people have tried to create approximations for the prime counting function. And the very first approximation that's ever been created was Gauss's approximation. And I'm going to call it GA for Gauss's approximation. And his approximation was x divided by the natural log of x. And he created that approximation when he was at a mere age of 15, which is very impressive. But yeah, so that's the very first approximation that there ever was. And the next approximation is lie of x. So lie of x, which stands for the logarithmic integral function, and it's the integral from 0 to x of 1 divided by natural log of t dt. So one thing to notice with this approximation is that it's undefined when t equals 0, because ln t, 0 is not defined, it doesn't exist. And it's also undefined when t equals 1, because ln of 1 equals 0, but then f of x equals 1 divided by 0, which again shoots off to infinity, so basically doesn't exist. And to overcome this problem, people created the capital lie of x. And it's essentially the same integral as the lowercase lie of x, but with different bounds. It goes from 2 to x, ignoring the area below 2 because of all the discontinuities. So what we're really interested in this video is this capital lie of x. So the first thing I'm going to do is define an integral which is very similar to this capital lie of x. I'm going to call it I sub n, and it's the integral from 2 to x of 1 divided by ln t, but to the power of n dt. And again, something to note here is that I of 1 is equal to the capital lie of x. Okay, so now I'm gonna try integration by parts on this. So I'm gonna let v equal to t, so dv is equal to 1. So I'm gonna let u equal to this, and du is basically the derivative of that. Sorry, this is meant to be dt there, du by dt. And I'm just going to tell you guys that the derivative is minus n divided by ln t to the power of n plus 1 times t. And you guys can check that for yourselves. So now carrying out integration by parts, what we get is u times v, which is t divided by ln t to the power of n, evaluated from 2 to x, minus the integral from 2 to x of v du. V is t times du, which is this here. And sorry, there's meant to be a dt here again. I keep missing that out. Ln t time to the power of n plus 1 times t dt. And this is I of n. So most things cancel out here, so the t's cancel out. The minus I bring outside to make a plus. And now I'm going to tidy this up. I of n. So this, evaluating that, we get x over ln x to the power of n minus 2 over ln 2 to the power of n plus, I'm going to take the n out, and then what remains is basically I sub n plus 1. Okay. I'm going to call this expression here a sub n. So therefore, to tidy things up even more, we've just figured out that I sub n is equal to a sub n plus n times I sub n plus 1. Okay, I'm going to clear up the whiteboard and I'll meet you then. Okay, so I've just cleared the whiteboard up. So now what we're going to do is, let me take that color. We're going to find I of 1, which is basically a1 plus 1 times I of 2. And then I of 2 is a of 2 plus 2 times I of 3. And then I of 3 is a of 3 plus 3 times I of 4. And you can see how we can just keep on iterating it like that. So now, you may think to yourselves, what if we substitute each of these values back into the previous iteration? What that'll give us is I of 1 equals a of 1 plus a2 plus 2 times a3 plus 3 times a sub 4 plus 4 times a sub 5 plus on and on and on, and a bunch of close brackets there. Okay, so simplifying it further, we get a1 plus a2 plus 2 times a3 plus, okay, so here we're going to get the a sub 4 term multiplied by the 3 and the 2. So 3 times 2, a4. And then here, the a5 is multiplied by 4, the 3 and the 2. 4 times 3 times 2 times a sub 5, and so on. And the pattern, you may have already noticed, is 0 factorial a1 plus 1 factorial a2 plus 2 factorial a3 plus 3 factorial a4 plus on and on and on. And because we have I1 on the left hand side, this is essentially lie of x, bearing in mind that I of 1 equals lie of x. And now in summation notation, what we find is that lie of x equals the summation of a of n times n minus 1 factorial from n is 1 to infinity. Okay, so now you guys are probably wondering, where the hell is my approximation to the prime counting function? Okay, so I have a bit of a confession to make here. So my approximation actually came by accident. I made a mistake when I went from this step to this step, and then obviously everything else was a mistake from there, and that made me find the approximation. And obviously I don't remember my mistake because no one remembers their mistake, but this mistake was actually really crucial because I found the approximation. So this is the approximation that I found. Okay, so this is the approximation right here. So what to notice from this approximation is that this is the same thing as x divided by ln x, which is Gauss's approximation. Add on this extra term x divided by ln x minus 1 squared. Okay, so I've tested this approximation to 10 to the 90 values using online software, and it seems to be wedged narrowly between Gauss's approximation and lie of x. And this makes me think that maybe, just maybe, this approximation that I have here, which is this here, could be asymptotic to pi of x, which I'm unable to prove as of yet, and I'm leaving it as an open challenge to all viewers to maybe investigate this further and look into it. But I thought this was really interesting. And one more thing, this series here is actually divergent, and you may be thinking, then how come it's approximating something that's finite? Well, that's because this is something known as an asymptotic expansion. What that means is that if we truncate this at a finite number of values, then we get a reasonably accurate approximation to lie of x. And that's how we get the asymptotic sign here. So yeah, so that's all I wanted to show you guys in this video. I think this is a very cool relation here, and I think this is a much more efficient way to calculate, to approximate pi of x, because computers can't do integrals. They don't know how to do integration. They use numerical techniques to do it, and obviously you can see how that'll become a problem for really big values for x. Whereas my function is more accurate than Gauss's function and easily calculates an approximation to pi of x for really large values of x in a computer. Okay, so as I said before, I'm just going to leave this for you guys to investigate more and maybe find more patterns to this or something. And as always, I'll see you guys in the next video. Take care. Bye.